Okay guys, let's try and understand laws of vibrating string. Now first of all, what we intend to check out is the fundamental frequency, formula for fundamental frequency. It is n is equal to 1 upon 2L root T over M, where we know T is tension, M is mass per unit length, and L is length of string, in which we have generated the frequency. Now let's check out law of length. In case of law of length, best example that we can take is of male and female voice. Now if we check out Adam's apple, in case of male, if you assume this to be Adam's apple, in the throat, this is the Adam's apple, and these are the two cords, vocal cords. Alright, now in case of men, we have longer vocal cord, whereas in case of female, we have, as they don't have Adam's apple, so they have shorter vocal cord. Now, so let's understand in terms of pitch, owing to which the frequency generated by vocal cord in male have low pitch or deep voice, or the frequency is around say 90 to 155 Hertz. Whereas in case of female, vocal cord is shorter. Now since the vocal cord is shorter, so more high pitch why? So more frequencies, so high pitch shrill voice, and the frequency is at around 165 to 255 Hertz, whereas in case of male it is 90 to 155 Hertz. Alright, so 90 to 155 Hertz, 165 to 255 Hertz. So that's the reason why male have deep voice, whereas female has shrill voice. Alright, so it all is why? It's all because of length of vocal cord in case of men is longer than in case of female. So follows N is inversely proportional to length. So longer the length, lower the frequency, so lower the pitch and deep voice of men. Alright, whereas in case of this, shorter the length, the higher the frequency, higher the pitch and shriller the voice. So by example of vocal cord of male and female, it's very much easy for us to understand the relationship of frequency with length. Alright, so inversely proportional. This can be tried out with strings also. Take a shorter string, would have shriller sound. Take a longer string, would have dull sound. Alright, now in case of law of tension. In case of law of tension, as the formula says, it is directly proportional to root of tension. So N is directly proportional to root of tension. Alright, so root of tension. If L and M are constant, here also when we talked about tension and mass per unit length have to be constant. Alright, now in case of law of tension, we can take an example of the string which passes around the pulley and is tied to weight. Now in this case it is tied to heavier weight, in this case it is tied to lighter weight. So heavier weight means higher tension, a lighter weight lower tension. Tension, as I told, is always towards the place where it is attached to a support. Now here it is attached, here the string is attached to support here, whereas here this string is attached to support here. So tension is moving up, here also tension is moving up. Tension in this case is greater than tension in this case. Why? Because weight is greater than W2 is greater than W1. So now if we try to plucker this string and plucker this string, obviously this would have shriller sound than this. Alright, that itself concludes that higher the tension, higher the frequency, higher the pitch, alright, or shriller the voice. Alright, so that's what it is, provided L and M are constant. Now in case of law of linear density. In case of law of linear density, N is inversely proportional to mass per unit length if T and L are constant. Now this is just a string, area of cross section of string, length of string. Now N is inversely proportional to mass per unit length. Now this is area of cross section and this is length. So volume would be pi r square L. We know that pi r square into L would be the volume. So density is equal to mass upon volume, we know. So mass is equal to, we will shift it there, pi r square L rho. Mass per unit length would be m over L, which is pi r square L into rho upon L. LL gets cancelled. So mass per unit length would be pi r square rho. This would be the formula for small m. Capital M I have taken it for mass and small m I have taken it for mass per unit length. So mass per unit length would be pi r square rho. Alright, so the formula can now also be written as frequency is directly proportional to 1 upon root of pi r square rho. Or if we take individually. So now when we talk in terms of radius, n is directly proportional to 1 upon r square. Now since root is there, so square disappears and it becomes 1 over r. So n becomes directly proportional to 1 over r. That is, n is inversely proportional to r. Now this we can also guess via wire. If a wire is thin, the radius is small, then it produces shrill sound. Whereas if the wire is thick, or rather the radius is more, then the wire creates dull sound. Alright, so ultimately what we can conclude is fundamental frequency n is inversely proportional to a radius of string. Then coming to density, we already have seen in the formula. Earlier we have seen that frequency is also inversely proportional to density. So frequency is inversely proportional to root of density. Now you may be wondering, how do we get this root? How do we get? Now these roots are found out experimentally. Alright. So n is inversely proportional to square root of density of material of vibrating string. Okay. Okay guys, it's all very much essential for you to know all these formulae individually. Alright. Because they may be asked in any format to be applied in numericals. Alright. Like they may ask you, initial frequency was this much given, and initial tension also given, final tension also given. So what would be the final frequency? Or it could be in terms of density also, ratios of densities or ratios of mass per unit length and so on and so forth. So please be well versed with all these formulae that we have derived. Okay, all the best.